Math 2414, Series Video 4, more example of geometric series. All right, so let's just take a look at some. But let's remind ourselves just exactly when a geometric series converges and when it converges. When it converges and what it converges to. If the absolute value of the ratio is less than 1, then well, let's write it in sigma notation. Sigma, we'll say k equals 0 to infinity of a times r to the k equals a over 1 minus r. Or more generically, the sum is equal to the first term once you've established that it's geometric and the ratio is small enough over 1 minus the ratio. To me, that's the more descriptive because saying first term over 1 minus ratio does not require that your series look like this. All right, so let's do it. All right, let's start with this first one. The sum from n equals 2 to infinity of 2 to the 2nth power times 3 to the n minus 1. When you see a series like this, where you have a product of things with exponents, and those exponents contain the n, one strategy is to break apart the argument until you have one number to the nth power. Now, how can you do that? Well, let's just take the argument to the side for a second, and let's see if we can write it as a number times another number to the nth power. And I just wrote that backwards, but I caught that now. All right, the first thing we want to do is get the exponents as by themselves as possible. For the 2 to the 2n, we could write it as 2 squared to the n. And for the 3 to the 1 minus n, we could write that as 3 to the first times 3 to the negative n by simply n adding the exponents. That means that we could write the 2 squared to the nth power as 4 to the n. The 3 to the 1 is just 3. And of course, the 3 to the negative n would be 1 over 3 to the n. And that means that we can merge the exponential parts together. The 4 to the n over 3 to the n we can put together as 4/3 to the n. And we have the 3 in front. So this series is the same as n equals 2 to infinity of 3 times 4/3 to the n. And again, my objective here was to write something to the nth power because that something is the ratio. Now, you might have been able to dig out the ratio by expanding the series and writing out a few terms, but if you can manipulate the argument into a number times another number to the nth power, then the number with the nth power is your ratio. And the first number may or may not be the first term. That's why I don't like writing this up here. The implication there is that a must be the first term. Well, guess what? The first term in this series is not 3. The first term in this series is what I get when I put in 2 for the n, which would be 2 to the 4th power times 3 to the 1st power, which is 48. So it's kind of a misconception that when you rewrite your sum in the form a times r to the k or r to the n or whatever the index is, that this number must be your first term, only if your sum starts at 0. So don't get so hung up on saying a is the first term because it won't be the first term. But we do know that the ratio is 4/3. And this problem is over. Why? Because the absolute value of r is greater than or equal to 1, and that means that the series diverges. So that ended pretty quickly. All right, let's take a look at the next one. All right, so let's take a look at this one, which you might think looks kind of the same and actually has an error that we'll fix here in just a moment. But it's not the same because the argument on this one is 2 to the nth power times 3 to the 1 minus 2n power, whereas on this one, it was 2 to the 2n power times 3 to the 1 minus n. Oh my gosh, I just realized I made a pretty catastrophic mistake in writing the problem, not in working the problem, because I've worked the problem exactly the way that I wanted. You might have noticed that we started with this, and then I immediately started manipulating this. But do you see the subtle difference between the two? The subtle yet important difference between the two? I turned the subtraction column around on the exponent. Why did I do that? Why did I do that? Because in my mind, when I was writing this problem down, this was actually supposed to be 1 minus n. It was not that way when I wrote it down. When I jumped into it, that's how I treated it. So I'm kind of glad I treated it that way, because this is what I wanted to go over this particular problem, where we ended up with a ratio that was too big and we got divergence. So if you were watching this the whole time and thinking, oh, you turned the subtraction problem around right there, you are right, but only because it was incorrectly written the first time. Let's make sure this one's okay. The subtraction problem is in the order that I want it, but there is one subtle issue with the sum. Can you see it? Variable in the argument does not match the index. And although this expression is actually defined, it's not what I wanted. I want the index to naturally match the variable in the argument, so we're going to go back and change this k to I can get this. There we go. All right, so we're going to do the same thing as before. We're going to try to massage this to have the form a times r to the n power, so that we can expose the ratio. That will always be the ratio. This a will not always be the first term, and that's why I don't like books saying you must look like this so that this will be your first term. Well, my first term is going to be whatever I get when I stick in the first number. Whether or not it's parked in front of the ratio is not nearly as important. But let's see if we can take this and massage it so that we can write it as a number times another number to the nth power. We'll do the same thing we did before. We'll break apart the 3 by writing 3 to the first times 3 to the negative 2 n. Then we can rewrite the 3 to the first as 3, and we can rewrite 3 to the negative 2n as 3 to the negative 2 to the nth power. Remember, I'm trying to extract the n from each exponent. Well, 3 to the negative 2 power is 1/9. And now we can multiply together the two factors that have the n as an exponent. And if we multiply those together, we get 3 times 2/9 to the nth power. Okay, so let's rewrite the sum so that it looks like that. This, all, get rid of you. And now let's just rewrite the sum. This is equal to the sum from n equals 1 to infinity of 3 times 2/9 power. All right. Now, is it possible to write the sum in one move? In other words, is it possible for you to look at this and go, oops, is it possible for you to look at this and say, well, it's the same as that? Of course it is. It's not nearly as hard as you think. You just got to keep track of everything. Who's in the exponent, who's not. But, you know, I would write it out until you're comfortable doing it. All right, so we do have a geometric series, and the ratio is 2/9. You know what the first term is? Not 3. The first term is what you would get when you start the series. So if we let n equal 1, we get 3 times 2/9 to the first, plus, that would be our first term. If we simplified that, it would be 6/9, which is 2/3. I really don't need to know the rest of the terms. I just need to know the first term. Here's my first term. Got the first term, got the ratio, and the absolute value of the ratio is less than 1, so we're good. And so we can draw a conclusion. Therefore, the series converges to the sum of the first term, which is 2/3, over 1 minus the ratio, which is 2/9. Don't you ever leave an answer like this. 1 minus 2/9 is 7/9. 2/3 divided by 7/9 is the same as 2/3 times 9/7. And if we reduce that and multiply, we get 6/7 for the sum. All right, let's take a look at one more where we have to massage the expression to locate the ratio and make sure that its absolute value is less than 1. And then if it is, then we can see what the series converges to. We have to restart the stopwatch. Oh, look at this mess. Sum from n equals 0 to infinity of -1 to the n times 3 to the n plus 1 over pi to the n minus 1 power. Well, notice that everything has an exponent. And one of them, the -1, has just an n. This is an alternating series. it has an alternator. But let's see if we can rewrite it so that we can rewrite the argument so that we have a number times a number to the nth power. All right. I challenge you to try to do this one mentally, but I'm going to go ahead and disassemble and reassemble this. The -1 already has the correct power. The 3 to the n plus 1 needs to be split up into 3 to the n times 3 to the 1. And the pi to the n minus 1 needs to be split up into pi to the n times pi to the -1. All right, so I've located all the pieces that have exponents of n. They are here, here, and here, so I can put all of them together. And the pieces that don't, I can just make the number in front. Now, because the pi to the -1 is in the denominator, I am going to move it upstairs to the numerator. That's what negative exponents do. They move you to the other side of the fraction. So the pi goes upstairs, becomes just a pi to the first, to go with the 3 to the first to make it 3 pi. And inside the parentheses, we have a -1 times 3 over pi, which is going to be -3 over pi. So that is the version of the argument that exposes the ratio, -3 over pi. All right, let's clean this up and then see if this is going to converge and then finish this. All right, so this is going to be the same as the sum from n equals 0 to infinity of 3 pi times -3 over pi to the nth power. And let's see what the first term is. Well, actually, let's start with the ratio, because if the ratio is not good, then we don't care what the first term is. The ratio is the number that's getting raised to a power, which is -3 over pi. And we need to see if the absolute value of the ratio is less than 1. Well, is it? The absolute value of -3 over pi is going to be 3 over pi. Is that less than 1? The answer is yes, because 3 is less than pi. Pi is about 3.14, so it's a little bit bigger than 3. So our ratio is pretty close to 1, but it's less than 1. That's all that matters. That means that it converges. It converges to the first term over 1 minus the ratio. Be careful, the ratio was -3 over pi. But what is the first term? Well, the first term is what we get when we put the lower limit in for the index inside the argument. Translation, put in 0 for n. 3 pi times -3 over pi, 0 power. This isn't as bad as it seems. -3 over pi to the 0 power is 1, so 3 pi times 1 is 3 pi. Downstairs, we have 1, double minus is a plus, 3 over pi. And that's a correct answer, but you should never ever leave a complex fraction answer, which is just a fraction inside of a fraction. In a case like that, you can just multiply both sides by the greatest common denominator of the little fractions, but the only little fraction is 3 over pi. So if we multiply both sides by pi, then on the top, we would get 3 pi squared. And on the bottom, if we distribute the pi, we would get pi plus 3. That's what our series would converge to. All right, so geometric series really aren't that bad if you can identify them. And if the ratio's absolute value is less than 1, then the series will converge to the first term over 1 minus the ratio. Just make sure you know what the first term is, because the first term is not always what's parked right in front of the ratio with the nth power. It happened to be that here only because we started at 0, but in the previous one, the number in front was 3, but the first term was not 3. First term is what you get when you plug in the lower limit.